Let's look at another phenomenon, that's straight light. Through all these reflections, we got straight light. First of all, straight light, because the lens surfaces are not perfect. It's never perfectly smooth, right? If you got 1/50th wavelengths, you still have some, okay, it's scattering. And then, of course, you can have dust that will scatter light. Therefore, even though one single surface reflects a little, but then you've got many surfaces, okay, so they add up. So you always have straight light in your lens system, and you reduce the contrast for you, okay? Now, another thing is even you have a perfect lens in here, no straight light from the lens. You still got straight light just because of the optical system. Now I'm drawing you a mask and go through a lens and into the wafer. So conjugate image, A goes to A prime, B goes to B prime, perfect. The problem comes is you got a reflecting plane, which let's say is a silicon, okay? Then your wafer and silicon. Now your image on top will be a mirror image at the bottom, vertical. And then this will reflect back, okay? It will reflect back. And you'll find that when you form the image, it images back to A triple prime here and B triple prime there. This beam is okay, it goes through, this beam is okay, it just goes out. This beam hits the chrome surface. Because of the reflectivity of the chrome, this is going to go back to the wafer and expose the place where you don't want it to be. That's straight line. That's straight line. Okay. So what do? You have to reduce the reflectivity of the chrome here. In the good old days, people just want good chrome, so their chrome was very bright. They can be over 50% reflection. So I went through this analysis, and I told people that no, you have to use low dark chrome. And people look at this, they don't understand it, and then they don't believe me. So I had to do some experiment to prove. It's not easy because if you don't have dark chrome, how do you prove that you got better performance with dark chrome? Okay. So here we did. Without dark chrome, we proved that with reflectivity. Here R equal to 66%, 16.7 and 10%, or 33 and 10%. Here we create some dark surfaces, and indeed we see our delta I, the sensitivity to illumination intensity is much better than this one. Okay, so how did I do it? These two I can get in the market. It's a bright chrome, it's a so-called dark chrome, 33. 10%. How do I get 10%? We coat the mask, a blank mask, no chrome. We coat a mask with photoresist, and we bake the resist until it carbonizes, which is something like 400 degrees. And 400 degrees, you burn the resist, you're completely oxidized. So what we did was we put it in a nitrogen oven, put in a nitrogen, no oxygen, and then we heat it to 400 degrees. It becomes carbonized. So that's dark carbon, and the reactivity is 10%. So we use it to prove. Nowadays, nobody will get this kind of reflectivity in their chrome mask. Mostly, they manage to have this kind of reflectivity. Okay, so the third, but the most important thing was this in the resist is illumination non-uniformity. It induces illumination non-uniformity. Let's explain what's going on. When you go into the resist, there's standing wave, right? Then you here in the dark part you got this intensity. In the bright part you got this intensity, which is a total of 26%. All right, and if I only change the thickness, resist by 50 nanometers, I create 26% of exposure non-uniformity. So even though I convert to 2.4 nanometer, I still have how much? I still have 2%. What was it? Oh, 2%. I have 2% intensity variation over very small distance. Okay. Now you said, oh, I can control the photoresist very well, keep it very uniform. But that's not the point. The point is that when you have wafer and you have topography, no matter how flat you can control the resist, you got yourself a thickness difference in the resist. And that gives you exposure difference. And it causes you a line width variation over the bar. Okay? All right. So far so good. Let's talk about meter, because if you cannot measure things quantitatively, you don't know how to improve things. So meter is very important. What do I want my meter to do? I want it to be able to monitor my edge position. Here is your nominal image, and here is the image that you just created. It may become a little bit smaller. It also is shifted a little bit. But all we care is that I want this edge, the edge of this thing, to be here. I want the edge of this thing to be here. And of course, nothing is perfect. So you talk about a tolerance. How much tolerance? We usually say, all right, if I want 10%, okay, if I allow it to vary by about 10%. So how do I control my things? So we plot this. In the defocus plane and the exposure plane, this is in log. So we plot these lines. Let's say this line is at 50%. That means if I adjust my focus and exposure along this line, my line width is going to increase by 50%. If I want a micron, 1 micron line, if I follow this line, I get a 1.5 micron line. If I follow this line, I get a 0.5 micron line. Okay, this is a constant line width contour, And then now I have 40, 30, 20, 10%, and so forth coming down. All right, so let's say if I want my line width to vary between plus and minus 10%, it is here. It's in this area. So if you can control your focus and your intensity within this zone, you're guaranteed to have your plus minus 10% line width control. Okay, but this is still not quantitative enough. We'll put a rectangle in here. We fit this rectangle into this zone, and say now, because if I'm here, I cannot. If I control my scanner, I can only control it in a rectangle fashion. Okay, otherwise it's impossible if I go out. So I need to put a rectangle in there, and then the length of this rectangle is my depth of focus, and the width of this is my exposure latitude. Okay, now you have yourself a very clear meter telling you how do you adjust your tool. In practice, we find that a rectangle is a little bit too pessimistic, so we turn it into all right. We turn the rectangle into an ellipse. I think here we turn it into an ellipse. And we find that ellipse is about 7 to 9 sigma. Okay, in a statistical manner. All right. Then I call, when I fit this ellipse in there, I call this long axis the exposure. I call this the depth of focus, and this is the exposure latitude. Okay. Now here I'm in the previous chart. I'm using a equal line and equal space as my pattern. Okay. And in this chart, I'm using 3 types of features. This is my equal line and equal space. I believe one of them is a contact hole. This is a contact hole. And this is an isolated island. Okay, we'll put all this together because when you have different patterns on the mask, you have to care about the common window. Because if you're not inside this common window is only this much. I have a window that's this big. But if I consider my contact holes and my islands, I have to take care of them too. So it only becomes this common window, and within this common window, you can put a rectangle in there or put an ellipse in there. Okay? And that is my meter. My meter is, sometimes I call it an ED forest or ED window, exposure defocus window. And using this technique, you can see the trade-off between focus and exposure. If you have zero tolerance in focus, you have a lot of exposure latitude. On the other way around, if you have no tolerance in exposure latitude, you have a lot of depth of focus. And somewhere in between, that you'll find a place that it is most optimum to use in practice. Okay. So with that, I'm going to use this measure to look at the world of lithography and quantify it. First of all, I had the equation, the resolution equal to K1 multiplied by lambda over NA and so forth. We use that equation and also the equation for depth of focus. Now we plot it this way, and we plot this line. This is a constant. This is a constant wavelength line. You keep the wavelength and then you change the NA, and that is what you get. When you have higher NA, you get better resolution, but then you lose depth of focus, and vice versa. I also plot a constant NA line and change the wavelength. And we can see when you change the wavelength, of course, shorter wavelength will give you better resolution, but less depth of focus. However, this curve is much slower than this curve, right? Yeah. So I keep on doing this. Then I have my lithography galaxy. This lithography galaxy tells you the entire lithography world between 365 nanometer and 157 nanometer. It also tells you between 0.95 NA and 0.35 NA. And you don't have to worry about anything outside. This is the world of lithography. That's all you can get between resolution and depth of focus. Okay? Now this lithography was plotted at K1 equal to 0.4. This lithography is not constant. It's not like astronomy, because you can move the galaxy. All right? Now, I'm moving this galaxy backwards. That means it becomes worse. What can make it worse? In a perfect system, if you have the mass vibrating or the wafer vibrating, you lose the image contrast, okay? And it moves backwards. Your galaxy moves back. Or if you have straight lights, as I explained before, if you have straight lights and this and that, it moves backwards. And that's why the IBM guys told me they want more than K1 equal to 0.8 in manufacturing, because they didn't control this. So when you go in and control this, you can bring K1 to equal to 0.64. You control the vibration, you control the refractivity, and this and that. And then you can do K1 equal to 0.65 as well as equivalent to K1 equal to 0.8. And of course, our purpose, we are not stopping there. We want to move. Yeah, that's what we did. We got rid of the straight line here and there. Now we want to move the galaxy forwards. Move it to K1 equal to 0.46 and K1 to 0.35. At that time, my vision was K1 equal to 0.35. I didn't realize that we can now push K1 to 0.3 and even slightly lower than 0.3. Okay, so. Okay, one of the applications is that you will find that there is always an optimum NA for your system. In the good old days, people tend to pay more money for high NA because they think they want to get that resolution. So, and also when you go to test a lens, right, test a stepper or a scanner, to play safe, I always look at a little bit higher NA to resolve my things, just to play it safe, right? But actually, that's wrong, because if we did that, if we use higher NA than we need, than here, then we lose depth of focus. You have to pick, even if you push very hard for very high NA, you tremendously lose your depth of focus. So it has to be somewhere in this region. But how do we determine that? Because we plot all these ED trees, we plot them and fit the elliptical windows in there. Now, when you have very high NA, you have a lot of exposure latitude, but not much depth of focus. When you have very low NA, you don't even have the exposure latitude. Here is the best. You have just the right amount of exposure latitude and give you pretty good depth of focus. Okay, that is the optimum NA. Here, somewhere here. And also there are different criteria. Maybe I want to optimize my depth of focus when I'm having trouble with depth of focus. Sometimes you have plenty of depth of focus, but then you want exposure latitude because you want to control your line width better. Then the criteria will be different, and the way you plot the ED trees will be different, and you end up with a different optimum NA for what you need. Okay? Okay, let's talk about phase shifting mask. Phase shifting mask, the way to create a phase shifting mask is that you would, normally you have this. Wavelengths get shortened in the quartz, and it comes out wavelengths in there. Here, if you add a piece of quartz in there, you prolong this optical distance, and then to the point that you have at this point 180-degree change in the outcoming light. That means if you look at it on this plane, you got yourself a phase shift of 180 degrees. Okay, so why do I want a phase shift of 180 degrees? Okay, this is no phase shift. I have an equal line and equal space pattern. This is my electric field, and then it's the electric field on the wafer. This is very square on the mask, but then it goes through the lens, and the higher spatial frequencies are filtered out. You are left with only the fundamental frequency, a single sine wave, and that's the electric field. And when you go to the photoresist only recognizes the intensity, not the phase. Therefore, it's proportional to the square of the electric field, and that's this. Okay? Now, when I have a phase shifting mask, it's changing every other pattern. I shift every other pattern to negative, -1. Positive 1, negative 1. This is 1 and 0, this is 1 and -1. So after it goes through that filter, spatial frequency filter, you end up with this. Again, a single sine wave, and when you go and double it in intensity, you get this. Much higher contrast. And that's how you use it to double the frequency of, let's say if originally when I do my best, my lens can only resolve half micron lines and half micron space. Putting a phase shift at every other place will give me 0.25 micron resolution. I'm reducing K1 by a factor of 2. Okay, that's another type of phase shifting mask. This phase shifting mask is very powerful. It's called a strong phase shifting mask. The problem with strong phase shifting mask is that you have restricted every other element. And when you are dealing with a two-dimensional case, it's not arbitrarily you cannot shift phase alternatively. You run into phase shifting conflicts. Okay, then you have to deal with. And if you don't want any phase shifting conflict, if you are completely arbitrary pattern, then you go to a phase shifting mask that look like this. It looks very much like an ordinary mask, except that it lets a little bit of intensity going through, and then it has phase shift by 180 degrees. So now instead of 1 and 0, you have 1 minus 0.1 and so forth. Well, still it improves your contrast and gives you a better image than before. The reason I brought this up is that this system is now it's now a baseline. It's well used in the industry. Almost always, when you want to improve things, you go to attenuate the phase shifting mask. Very popular. Okay, optic illumination. You can do the frequency doubling trick also with your illumination. Here, let's say if you don't have any angle, right? Let's go through there, and it got split into first order beam and zero order beam. And if this lens is not big enough, it will not resolve this light. It will kick it out. Now, if you tilt this, and it will shift all these 3 beams this way. Okay. Now your 2 beams now will be accepted by this lens and resolved by this lens. You are using these instead of that. So you are doubling the frequency. Again, half micron line, now you can use it to resolve quarter micron line. And also with this, you don't have to worry about phase conflicts in the phase shift mask. So it's also very powerful. Nowadays, when you go to higher resolution, you don't find any actual illumination. Everything is off-axis illumination. Okay. And people also play this too. It's optimal. It's no longer that simple. You have many different vectors to optimize the specific patterns you are interested in. So it becomes very sophisticated, and also it becomes quite costly. Okay, proximity corrections. If we don't do anything, this is the original mask pattern, and that's what you came out. You've got things joining, and then you've got line end shortening, thinning, and corners rounding. And here, when you've got an isolated line, it becomes narrower, and it becomes rounded, and you even lose some patterns. Okay, so you have to try to correct it on the mask. For example, you have to make this hole bigger, and make it bigger unproportionally, non-linearly against all these patterns and so forth. When you do this, you can end up with this. This is before any correction, and this is with corrections. Okay? Again, this also becomes $1 billion industry for lithography. You have to deal with, let's say, 10 nanometer technology, and the mask has a lot of pixels, 10 to the 12, 13 number of pixels, and you have to correct all those, and you do that in reasonable cycle time. So you have to do it at very high order of correction, and you have to do it very fast to get this. And not only optical, even if you're doing etching, you try to etch these, because here you've got higher density of the etch pattern, you consume your reactive gas faster than here. So you etch slower here than there. That becomes a problem, because for etching you also have to do proximity correction, and etching is not as predictable as optical lithography. They don't have Maxwell equation in etching. Okay, so it's tough. It's tough to correct all the way to etching. We're all using empirical means to proximity correct by etching. Okay. Now, even simple things like this, you add some sub-resolution bars in there that you are not going to print, but it helps you fool the system to think that it is within certain spatial frequency range. So originally, if you have this, when you add scattering bar, you have this window much bigger. And if you do it more optimized way, you have even this. And from this 1.2, from 60 micron, 0.6 micron to 1.26 micron. You stretch the performance by more than a factor of 2. Okay, now only a few slides will be over. Immersion lithography is not as simple as I'm going to show you, but let me show you a simple way. This is a dry system. All you need to do is, in an immersion lithography system, you want to put some liquid in between the lens and the photoresist. Then just make sure that the media that you pass through the lens to the resist would be higher index than air, and then you improve your resolution. In reality, people use something called immersion hood that would trap this fluid in there, and because you have to scan this stage, you have to move this all over on the wafer. This hood will keep the fluid confined within this area and will move the fluid along when you expose. Okay. And the theory is that if you don't have any water in here, if I'm pushing the angle to very high, let's say I'm pushing my angle to 0.83, it will not be able to pass through this combination. It will be totally internally reflected. Okay. The only thing that can go through is sin theta equal 0.58. Then you go through this this media and goes into resist, which gives you 0.51 angle. Now, with the water in there, then your 0.83 light will not be totally internally reflected. It's passed through, and then you get it resolved on the resistor. So it's just very simple. Before that, it was just rejected when you have the wrong medium in here. When you put the right medium in there, it lets the light go through and it gives you the resolution. And depth of focus is the same thing. I'm keeping this resolution, the same resolution at 0.58, but now this angle is very steep, this angle is less steep. I end up with more tolerance of the thickness change of this here, so I have better depth of focus. Okay, so this is my last slide. We look at how lithography changes. Initially, we're dealing with 0.8 K1. We use very low NA. At that time, we think 0.15 NA is also already very difficult because you have to do the lens perfectly. Okay, everything has to be perfect. So 0.15 and at a 463 nanometer wavelength. Then we think the resolution has room to improve, so we push the lens all the way to 0.45 NA, keeping the 0.8 K1. Then we're saying it's very tough to increase this NA. So we reduce the wavelength to 365. And we reduce the NA, still at the same 0.8 K1. And now we push this NA to 0.65, and also we have to pick up some K1, 0.8 to 0.6. We're already dealing with this here. That is what? That is about 300 nanometer, isn't it? It's already below wavelength. Okay, 365 is my wavelength. This is only 300. Okay, then we keep on going. Well, actually, this is my wavelength line. This is my wavelength line. And this, we're pushing I9 lithography a little bit lower than the wavelength. And 248, we stay at 0.6 K1, and then we are relaxing the NA to 0.35. We gain depth of focus that way. And then we keep on pushing it until we reach 0.82 NA and 0.4 K1, and it's way below wavelengths. In argon fluoride, we cannot allow anything even equal to wavelengths. Everything was sub-wavelengths. Okay? And with argon fluoride, we push all the way to NA equal to 1.35 and 0.3 K1. So what did we do? We were hoping that at this point, EUV will come in, but it didn't come in. And 157, of course, is already surpassed by immersion. Therefore, the only way we could do was to use double patterning. That means to expose the same pitch twice, but at an offset. This way, you're creating double pitch. And this way, we cut the K1 by half, 0.15 K1. Okay, with a single exposure, there's no image of 0.1 K1. Now, but with double exposure, now you can push it to 0.15 K1. Now we are doing more than double patterning. We're doing triple patterning, we're doing quadruple patterning. So therefore, your K1 equal to 0.3, now is 0.075. All right. Okay, now, EUV. EUV, it was supposed to take care of 100 nanometer, but it didn't happen. Okay, at a very relaxed NA and very high K1. We're hoping that it will enter here. It didn't happen. Now we're hoping that it will happen here. If it doesn't, now notice we didn't put 0.3 K1 here. We put 0.4 because with EUV the wavelength ratio is short. The straight line and other things is more difficult. It's much more difficult to get a smooth surface because the wavelength is much shorter. Okay, so it probably would end at 0.4 K1 instead of 0.3. Therefore, at this point, we have to double pattern EUV to keep going up. So that's what's happening. With this, I thank you for your attention. Thank you.